Hey, this is Dr. B, and let's consider spontaneous processes. Chemists like to consider whether something might happen spontaneously or not. For example, if you formed a certain substance in a chemical reaction, would it spontaneously, I don't know, explode? That's something that, a chemist would be concerned about. So let's evaluate this. Let's start with some pretty straightforward considerations. A spontaneous physical or chemical process. Tell me, would it happen spontaneously? Would a waterfall run downhill spontaneously? I think so. Would a lump of sugar, if you throw it in coffee spontaneously dissolve? It would. If you're at sea level, will water freeze when you get below 0 degrees Celsius and melt as soon as it gets above? It does always. Will heat flow from a colder object to a warmer object? Careful, I think that's backwards. If you shake somebody's hand and his is warmer than yours, you get some of his heat. So no, but the opposite is spontaneous. If you have a system like this and you open it up and there's no pressure there, will it mix? It will. If you got iron and you expose it to some oxygen with a little bit of water, I didn't really know the water was needed. Apparently it is. Will it rust? It will. All those are, as long as you do them in the right order, spontaneous processes, and everybody usually says, yeah, I do that. Now, trust me that every single one of these is a spontaneous process, and here's the energy values. Something's funky there. Do you see it? Like, a couple of them are positive. They're endothermic, and yet we hear that they're spontaneous. How could that be, right? So what can we conclude? This is getting a little ahead, but I did make a little note here that in every one of these, the free energy is negative. That's what it means when it's spontaneous. This value known as Gibbs free energy. When it's negative, you got a spontaneous process. Fine. Well, I think we can say that spontaneous reactions don't all release heat to the surroundings. Some of them are endothermic. Something else must play a role, and the term that we're going to see, and I'm going to go ahead and go to the next slide, is known as entropy. Maybe that's a new term for you. Maybe you're hearing it for the first time. Let's cover it from the beginning. Entropy is defined as just when things get a little bit more random or more disordered. College textbooks like to call these things microstates and things like that. I find this a very clear way to understand entropy. So, if things increase in their random, like your room gets more messy, the value of delta S is defined as positive, okay? So, positive change in entropy means things are getting more random. You can solve so many things just from considering the regular state of stuff. So let's predict the relative entropy values for solids, liquids, and gases. Well, gases are going to have the most degree of disorder, so they're getting higher as you go to a gas, right? I'd probably throw this in reverse. So that's good. So how about the sign of delta S if you're melting some water? No, we're freezing it. I think it's going to be negative, right? How about if you dissolve something? Doesn't this look more random than this? Yeah, I think so. So I think the entropy increases when you dissolve stuff. I do remember something from graduate school where they talked about water going around DNA and doing it in an incredibly ordered fashion. Not dissolving it, but the water molecules going around it, in which case the entropy was getting very much more negative. But that's a different situation. We're simply dissolving this. Okay, fine. Now let's talk about, for chemical reactions, trying to predict it. One quick thing is that if you're decomposing something, it's generally speaking going to become more random, right? If you're synthesizing something, two things turn into one, it's getting more ordered. But we can also consider this from the point of view of gases as well. If you're making more gas molecules than you've consumed, you are getting more random. Yeah, making more gases. If the total number of gas molecules is going down, you're getting more ordered, negative delta S. If there's no change in the number of gas molecules, it's probably not going to be a very big number. So let's do it. Let's have a look at this one. Well, first thing is it's a synthesis reaction. 2 turn into 1. I think that's going to be more ordered. Delta S is negative. Also, the gas molecules are going away completely. It's negative. Here we have a, tell me what you think of this one. This is a decomposition reaction. One thing turns into two, and they're both gases, so definitely getting more random. Positive. How about this one? We got a gas and a gas making a gas, and it's also looks like a synthesis reaction, but check out the number of molecules. One molecule plus one molecule does make two molecules. So we're not changing the number of molecules, and they're all gases. So I'd say it's either going to be 0 or relatively small in some direction, not much of a change. This is an introduction to entropy.